Yeah, thanks a lot. It's great to be here. Yeah, the title of my talk is what is a good use case for quantum computing? And I mean, who was there previously, saw already like a lot of discussion. And we might have a little bit different view on quantum computing than what other speakers expressed, but I will get there. Let me say first some words on on our company. Our company was founded in 2017, and we started working for companies like BASF and Bosch in the field of quantum chemistry, where the goal was to really see how quantum chemistry could profit from using quantum computers. So from the very first moment, it was about seeing how use cases could be realized on a quantum computer and how to identify them and how to really see how this would look in a workflow. And in the meanwhile, we also work on finished software products. So we have delivered software for quantum computing, but this is mostly, I would say, academic use cases. And we also make simulation software for quantum mechanical problems. And today, this is what we do. We make software for spectroscopy in chemistry, and we still work on the identification of use cases. And this is what I want to talk about mostly. And if we look at a use case or ask ourselves, is this problem a good use case for a quantum computer? We always go through 4 steps. First, we ask ourselves, is there really somebody who wants the solution to this problem? I mean, is somebody really interested? And this might seem obvious. However, in the field of quantum computing, there is a big topic where people actually analyze purely abstract mathematical problems and see if the quantum computer is faster for these problems. That's a fair kind of benchmarking type of work done in academia. So it's reasonable to do it, but of course, for us, we want to have a problem. It doesn't strictly need to be industry, but people need to care about the result and not just about the fact that it's cool to run it on a quantum computer. Then there are 2 important steps. You need to really think about how to bring your problem to the quantum computer. Then you also want to really have the best classical software as a comparison benchmark. And at the end, you want to, of course, make sure that this really will lead to quantum advantage. And if I would shorten this, we call this identify, transform, benchmark, and quantum advantage. So ITBQ. So we shorten it. And there are 2 steps I want to emphasize that are often, we feel, not done sufficiently or not thought enough sufficiently. This is transform, where you think about what is the best way really to pick out a subpart of your problem or transform it mathematically to map it to qubits. And benchmarking is also quite important. It also has the advantage if you directly build up the best classical software stack, you have the best classical software stack. So that's also great. But now let me say, of course, if you look at these 4 steps, you don't work through this like step by step in practice. Yeah? Especially in many ways, if you look at the problem, somebody comes to you and say, oh, I want to solve this problem, it's very hard currently. You can directly normally look a little bit at this and ask yourself, do I believe that I should ever use a quantum computer to solve this? Yeah? So we have a feeling what fundamentally can achieve quantum advantage. And so directly when looking at the problem, you can make a little bit or gain a little bit of a feeling for this. And generally, we do this by, we don't ask ourselves, is the problem fast or slow? But by asking us, how would it scale? How would it scale on a classical computer? And how would it scale on a quantum computer? And I think people might seen this type of plots I show here. These are these typical exponential scaling plots I show here. And what you want is that your problem goes from something that looks in scaling like the orange curve on a classical computer to ideally the magenta curve on the quantum computer. And then we can look a little bit already through these typical problems you constantly hear about for quantum computing. Optimization, machine learning, and quantum simulation. And I just give you also the HQS view on this. And this is that basically, what do we know about scaling? We do not expect better scaling for optimization. Machine learning is super interesting. There's a lot, I think, work to do. But personally, I'm optimistic. And of course, we expect better scaling for problems that are intrinsically quantum mechanical. That's why often these problems are in chemistry industry or in material science. Because if we want to simulate things on the quantum mechanical level, this is needed in industries like chemistry and so on. So basically, this actually gives you directly a little bit of a feeling once you pick out a certain problem about the probability of achieving a real scaling advantage. And this is, of course, based on the ability to fundamentally prove if there is any better scaling to be expected. Of course, this is not always possible, but given that quantum computers are currently still in this infancy, there isn't really the possibility to try things out a lot. So we have to start from like a sound understanding of where to expect, where we have a high probability for quantum advantage. And now I want to show you a little bit these 4 steps for one exemplary use case where we have worked on. So we have worked basically from 2019 almost when we started to today with Merck on a use case in quantum simulation. It started out more as a general simulation study on molecules. And then as we investigated it further and sharpened every step, we went into this direction of simulating NMR spectroscopy. And today, we still work on this, and also we work on it in a sense that our customer doesn't really care how we solve it, classical or quantum computer or anything. The most important thing is that it gets solved because it's fundamentally important. Now, I think I need to explain a little bit what this use case is. So what is this use case, NMR spectroscopy? This is a technique that is widely used in pharma and chemistry. You use a device that looks like this picture here. This picture here. There you put in normally like a liquid. In this liquid you have solved some molecule, and then you put this in a very strong magnetic field and irradiate it with microwaves, and then measure again what kind of microwaves go in and what kind of microwaves go out. And from this you get a spectrum, meaning you get various frequencies, and at these frequencies you see some kind of microwaves are coming back at a certain frequencies. And then we look at this and say, oh yeah, there are all these peaks here. And immediately we understand, oh yeah, that's menthol. And of course we don't do that. Yeah, I mean, it's actually really complicated to interpret kind of what these peaks mean and why these peaks indicate that this is menthol. Now, people have been doing this for 50 years because there are, of course, techniques to connect this spectrum to this molecule. But actually, even to this day, this is quite complicated. So I would say it's an unsolved problem to make this really reliable, fast, easy, especially as your molecules become bigger, and also if your magnetic fields become lower, which people want because it's cheaper. And so this is a really clearly defined industry problem. You want to know, if I have a certain molecule, what is the spectrum? This is a simulation problem. And then you can say, okay, this molecule gives me this spectrum. I compare to my experiment. Do I have what I expect to have? Of course, at some point, you would also like to turn this around. I give you the spectrum. You give me the molecule, or your code or your program gives you the molecule. But a good starting point is, for a given molecule, what would the spectrum be? And now I want to discuss directly why we found this immediately super fascinating as an issue. It's an industry problem, but why did we think, oh, that looks really cool for quantum computing as well? So the fundamental degree of freedom, so yeah, let me directly jump to this point a little bit. Why is it a good use case for quantum computers? So the fundamental object you look at in this type of spectroscopy is the spin, the nuclear spin. So it's the nuclear spin of hydrogen atoms that is being measured. So what you saw in these peaks is the response of these nuclear spins to being basically excited through microwave radiation. And now the plot, what I'm drawing here, is supposed to indicate to you that the spin and the quantum mechanical bit are actually mathematically the same. Yeah? And I think most of you have probably seen this sphere as a way to depict qubits. Yeah? The state of a qubit as this arrow on a sphere. This has been shown in publications also for the broader public broadly. But actually, it turns out that this sphere, so this sphere actually has a name, it's called the Bloch sphere, and it was first drawn for nuclear magnetic resonance. Yeah, so to explain effects and features people measured in nuclear magnetic resonance, they depicted this using the sphere. So they depicted the spin using the sphere. So actually, it comes from nuclear magnetic resonance, and we use it today because it's very practical and mathematically relevant, also to describe qubits. So they are equivalent, so the mapping is perfect. Yeah, so it's as close as just taking the quantum computer and letting it time evolve. It's still a little more, unfortunately, but it's as close as it can get if you have a problem. And there's the computer, okay, so sorry. So now, here is the spectrum, yeah? So here, this is how this looks. This was run on a quantum computer. These black lines are what it should be. The orange lines are what we get. So this was run, actually this is already 2 years old. This was run on IonQ through Amazon Bracket. So it's pretty straightforward. So it's doable, and now for people a bit more mathematically inclined, let me show you the equation, what you have to do. So this is the quantity you have to calculate, and what I want to emphasize is this U of t is a unitary operator, so this is the time evolution of a quantum mechanical spin model. So it's the most obvious thing that you can imagine or prove that the quantum computer will have exponential speedup. And then you actually sample this sum here. So it's a scattering problem on a unitary operator, okay? And so for people who have looked maybe in the literature on quantum advantage, scattering problems on unitary matrices are also the most obvious problems for quantum advantage. So on many fronts, on terms of fundamental conviction that this will achieve quantum advantage if quantum computers get bigger and better, I mean, it doesn't get any more solid than this. Now, as I promised, transform. I still have 6 minutes, so that's good. A transform, why does this matter so much? And I want to show you here, or why do I feel that this matters so much? I want to show you what we do here when we do this, because let's say somebody who wants to solve this type of problem would normally specify a molecule, for example, as this picture here. And they would say, this is my molecule. This is a 2D picture, standardized, it uniquely represents most molecules. But you know, from this, you need to squeeze out parameters that later go to the quantum computer. Yeah? Or again, for the fans of quantum computing or quantum mechanics, you have to squeeze out this type of spin Hamiltonian. And from this, you can then calculate the spectrum, be it classically or be it on the quantum computer. And now, we have built a huge infrastructure to actually do this, yeah? Where you first take this structure and then have a kind of approximative way to very quickly generate a 3D structure. So this would be, for example, an initial 3D structure. This is for penicillin, a very well-known molecule. And then you start to sample many of these structures because the experiment is actually slow, so it averages over many of the structures of this molecule. So you have to sample overall various structures, and then also all conformers. These are kind of rotational conformers where you take one of these groups and start to rotate it. And then at the very end of this procedure, you get out these NMR parameters. And actually, when it comes to NMR, this tool chain and this workflow is where the major manpower goes in at HQS. So it's actually this step, because everything else that flows afterwards on the quantum computer relies on this being good. Because if this is not good, the next step will also not be good. So this is where the major manpower actually goes in when it comes to NMR, and I just show some pictures where we show we can do it. This is all solved classically. So this a spectrum where you see here the black line and the orange line all look stood together, but the orange line was calculated not on a quantum computer, but classically, and this, of course, comes to the other very important point, good classical benchmarks. So I want to show you this. So here we actually got some measurements from friends of ours for a 50-spin molecule, and this was really cool because, as you might know, 50 spins is always considered like the limit of what classically is possible. So I say, okay, 50 spins, amazing, this is going to be quantum advantage. But of course, we set out to calculate this spectrum here for this molecule fridolin, also classically. I say, okay, maybe we can actually classically simulate 50 spins after all, and how do we do it? You look at this. Okay, so first of all, fridolin was also quite nice because you can get good parameters because it's very stiff, so it's not rotating so much, so you don't have to do that much conformational sampling. But then, of course, a key point is you can use techniques like clusterization, because if you have a nuclear spin at a hydrogen atom here, it doesn't necessarily need to know what the hydrogen atom here does. And this we implemented in a very black box fashion. And it turns out that this clusterization converges pretty quickly for this molecule, and we are able to simulate all 50 spins using certain clusterization techniques. So the bad thing is this molecule and its spectrum is not something that we could solve on a quantum computer and achieve quantum advantage. However, the good part is we have an amazing classical solver and can solve all types of stuff classically. Also good, yeah, very nice. And there are also use cases where clusterization fundamentally doesn't work. So this is, for example, in phosphor chemistry. There's a one molecule phosphor chemistry is, for example, important for fertilizers, where you have two phosphor atoms. And here we show the exact spectrum with these two orange peaks here. And if we even go to very large cluster sizes, we still get a qualitatively wrong spectrum. So this is really fundamentally at all cluster sizes, this does not converge. You need every spin sees every other, so this does exist. We could still solve this classically. It has only 22 spins. Actually already pretty hard to solve, but possible. But what I'm saying is that there are definitely cases that we need the quantum computer. And with this, I want to stop here and just say we are actually, if you're interested also as a quantum computing enthusiast or so, to look at these NMR problems or other spectroscopy problems, we are going to publish these benchmark problems in terms of really the Hamiltonian. So not on a very kind of on a really low level, meaning you can just directly take the Hamiltonian and shove it in your quantum simulation, whatever that is. So it's going to happen very soon, and we're going to do 2 more use cases: electron spectroscopy and magnetic response. These are all spectroscopy use cases. And if you want to follow us on LinkedIn, you can find the link here. You can contact me, of course. And we're also going to make a workshop on these use cases in Karlsruhe for people who are interested in November. So thanks a lot. And with this, I'm finished.